Okay, we're at calculus class. We're going to give you a test back after we go through this, the front part of this lesson. You guys need to be aware that this is a 3-day lesson. This is not a 1-day lesson. So we started with a big idea when we started this class, and as we went through it, it kind of got a little bit easier for you guys to understand the concept of limits. Today we're looking at the precise definition of a limit. There's definitely going to be moments you are going to be confused, okay? All right? And that confusion will get better tomorrow and then on Friday as well. So please show patience. Y'all understand where we're going to be at? Let's investigate, okay? We want to look at this function right here, okay? I'm going to type this in. We're going to go to y equals. You don't have to. You can just follow along. I'm going to type in 5 parentheses x minus pi to the 4th power times the sine of 10x. And it looks like I'm working in radians, which is great. And I'm going to divide that guy by x. And I'm looking at the limit as x approaches 0. I'm looking at the limit as x approaches 0. Okay? Y'all okay with that? Why don't I just plug in 0 to evaluate it? Yeah, you get 0 over 0 because the sine of 0 is 0. And you have 0 in the denominator. There's no way to really reconcile that. So maybe we could look at the graph and figure out what it's doing. So I'm going to zoom standard. And I'm going to look at the graph. So as x approaches 0, is it clear to you what the limit is? No, it's not, is it? So what's another way that you learned that you could try to examine the limit? Okay, look at the table. All right, I like what SB is doing. So what should I type in here? Okay, negative 0.1, negative 0.01, negative 0.001. And it looks like I got 4,876.6. If I try negative 0.0001, looks like negative 4,870 something, huh? Maybe if I try from the positive side, I try 0.1, 0.01, 0.001. Looks like that 4,800 is probably a pretty important spot, isn't it? In fact, I'm going to change my window so that my x minimum is just going to be negative 1. My x max is going to be positive 1. And my y values, what did we say it was? 4,000? Oh, 800? We'll try 4,900. See if this helps us a little bit. So if I, again, check that window of those scales, instead of having every one, maybe we go like every 1,000. Again, I just want to look at that table value, see where we were at. 4,870 something. So again, we check my window, 4,800, and let's try like 50, or maybe even 60, and 4,900. Let's see if we can see the graph better. Come on. Still looks like it goes a little bit higher there, doesn't it? Let's try the window. Let's zoom in a little bit more. Negative 0.01 and 0.0. Whoop. See if that helps. Let's try to zoom into a smaller region. See if we can see what the heck is going on. Oh, kind of see it now, huh? There it is. I mean, if I press trace now, would everybody agree that right now, like, you could be convinced at this point finally that it looks like the limit might be around 4,870, somewhere around there? Somewhere around, we're just doing it like somewhere around 4,870. I mean, honestly, it could be like, you know, a plus or minus of about 5 units for all I know. It's somewhere around there. But wouldn't you agree that this looks like a pretty difficult limit to identify? So when we say our current definition of limit or phrase, we say is x approaches 0, f of x gets closer to some limit. And why are these phrases problematic? Well, these phrases are problematic because a few reasons. You have crazy functions. And second of all, and this is the most important one, it raises a question. Oh, you crazy functions. Ah, you bunch of crazy functions. It raises this second question, which is really problematic, and that is how close must we get to x in order to be confident in our limit? How close do we have to get to x? You guys pick values like 0.1 and then 0.01 and 0.001 and 0.0001. Now, at first glance, you say, well, those look like they're pretty small values. Like that would be enough. Who is to say that's really enough? Maybe it really depends more on the type of function that we're looking at. How can we be certain that the limit is what we're stating it is? This is difficult to understand, but this is the best way to summarize it. How close do we have to get to x in order to ensure that that limit is where we want it to be? And this is where the proof of a limit comes into play. We need a precise definition of a limit, and you're going to have to memorize this perfectly for the next test. Please understand that I have taught this course many, many times. Your first reaction will be, that would be ridiculous for us to be able to memorize it. That will be your immediate reaction. You need to trust me that I've gotten everybody to memorize this with really no problems. I would say in a given year, it's usually about 1 out of 30 people messes up a little bit on the test. Everybody else gets it right. Sorry for you, 1 out of 30. It helps if you draw a picture to go along with it. And it starts like this. Let there be a function. Let there be light. Defined on an open interval. Can the limit exist even if you have an open circle? Yes. So let there be a function defined on an open interval, but maybe not at point A. Let there be a function defined on an interval, but maybe not at point A. You could have an open circle here. It could be closed or open. Doesn't matter. Then the limit as x approaches A of the function is equal to L. Let there be a function defined on an open interval, maybe not at point A. then the limit as x goes to a of the function is equal to L. If for every epsilon, Greek letter for E, greater than 0, what is epsilon? Epsilon is the value above or below the limit. So this would be L plus epsilon, and the bottom would be L minus epsilon. If for every epsilon greater than 0, there is a delta greater than 0. Epsilon is the distance from the limit. Delta is the distance from A. This is A plus delta. This is A minus delta. That satisfies absolute value of f of x minus the limit is less than epsilon whenever absolute value of x minus a is less than delta. Done. Now, as you finish up writing it, I'm going to have you practice memorizing a certain part of it. And I want you to understand, I hate memorizing just for the sake of memorizing. You won't be able to do certain problems on a test unless you have this memorized, because you actually make use of this. And I'm going to show you the best way in which I think you actually remember it. Is everybody done writing it? Just say broad shoulders. Mr. Gens, your shoulders are too broad. You're too strong. Please move. We good? Watch. Here you go. Let there be a function defined on an open interval, but maybe not at point A. Then the limit as x approaches A of the function is equal to what? L. If for every epsilon greater than 0, there is a delta greater than 0. See how I draw it? Let there be a function defined on an interval, maybe not at A. Then the limit as x goes A of the function is equal to L if for every epsilon greater than 0, there's a delta greater than 0. The picture goes along with it. You don't have to do the ending, but take it up to the delta greater than 0. You have 2 minutes to try to memorize this as best you can, and you're going to try to recite it to a partner. Memorize it. Ready, set, go. Let's try it. Take out your notes. Let's give one a shot. It says, consider the function f of x is equal to 1 over 2x. Find an interval for x values such that the y values will always be within 0.2 of the limit as x goes to 2. This is the idea, folks. Here's what it means. Notice this previous problem that we looked at. In order to be confident of that limit, do you all agree that we eventually had to zoom in to a certain window? Well, here's the deal. You would like to zoom in really close. In fact, you'd like to zoom into an interval of 1 over infinity, a super small value. And mathematically, we're actually capable of doing that. Before we do that, we're going to start looking at just general values. So what you want to look at is when you see this crazy thing right here, this is a window in which we are zooming. We are going to take epsilon super small. We're going to have epsilon be like 0.0001. And that's going to create delta smaller, and we're going to zoom around that singular point right there to ensure that the limit is perfect, exactly what we think it is. And so here you have it. It says, consider this function, f of x is 1 over 2x. What does that look like? Very good. Always write the limit of whatever we're talking about. The limit as x approaches what? 2. Where'd you get that? So as x approaches 2. Of the function, what's the function? 1 over 2x is equal to, can you find that limit? Can you plug in 2 and get a value? What do you get? You get a 4th. We know the stinking limit. Which letter represents 2? What letter have we used that represents 2? A. What letter represents 0.25? L. Epsilon. Find an interval for x values such that the y values will always be within 0.2. Epsilon goes with y values within 0.2. So I'm going to go up 0.2. If I go up 0.2, where am I at? Exactly. 0.2 would bring me to 0.45. Is everybody okay with that? Watch. As I draw this over to the function, do I land to the right or the left of 2? Everybody agree that there's an x value right here. There's an x value right here such that when I plug it into the function, I get 0.45. We're going to find that. And it's very simple. You take the function, and you set it equal to 0.45. Will we be able to find x now? How could you find x? Cross multiply. 2 times 0.45 is 0.9x equals 1. Divide both sides by 0.9, and you get x is 1.1 repeating, or 10/9. Now, I know that this doesn't look to scale because 10/9 is behind 1, but, you know, it's not drawn perfectly, but you could see it's behind 2, right? So 10/9 is my first x value. I'm going to find another x value. Instead of going up 0.2, I'm going to go down 0.2. And where's that going to bring me? 0.05. Look at where that brings me to the curve. Is it to the right or the left of 2? To the right. I'm going to find out what that x value is. How do I do that? 1 over 2x equals 0.05 over 1. Now what? Cross multiply, and I get 0.1x is equal to 1. Divide by 0.1, and I get x is 10. This is what's really important. You found the x values, but it's saying find an interval for x values. We're looking for a delta value. Notice what our definition says, folks. The definition says The limit exists if for every epsilon greater than 0, there is a delta greater than 0. Well, we have an epsilon. What's our epsilon? 0.2. So we're going to find a delta. Delta is the distance between the x values and your a value. What's the distance between 2 and 10? 8. What's the distance between 10 ninths and 18 ninths? 8 ninths. Which one is smaller, 8 ninths or 8? 8 ninths. You choose the smaller of the two. Delta is 8 ninths. What this means is very simple. If you simply go 8 ninths to either side of that, of 2, your outputs will always be within 0.2 and 0.25. This curve will never bounce outside of that y value. You know you don't have to zoom in anymore. It will always stay within that region, and you could nicely look at it and be able to say, oh, it's 0.25. If you weren't convinced, guess what you could do? You could zoom in even smaller and say, oh yeah, it's not going to bounce outside that window. You could bounce in even smaller and say it's not going to go outside that window. We can carry our window eventually, not today, to 1 over infinity in terms of width, which is mind-blowing. Today, what you want to do is take your worksheet. You want to look at the function, look at the a value and the L value, the epsilon, and you're going to find the delta. Today, your goal is to find the delta. Tomorrow and the next day, we're going to talk about more what it means, and it will eventually fully connect for you. This is the one study I saw. It was my sophomore year in pre-calculus. My teacher taught it to me, and at that point, it was a defining moment. I knew I was going to be a math major. There's something beautiful about the epsilon and delta. And I've had a few students who say after about 5 minutes, like, oh yeah, I fully understand it. You probably don't. In fact, there's many of you that may not understand it fully after 2-3 days. But allow the problem to kind of sink in and analyze it, and hopefully it'll come to you. We'll take some time with it. Here's your worksheet.